In this video, we're gonna discuss maximal subfields of central division algebras. Let us motivate that by the question of splitting. We know that a central division algebra always split over some field, for example, the algebraic closure of K, but we might be greedy and want more than just any splitting field. We might want splitting fields for D that actually lie inside D. So the question is, does D split over any of its subfield? Well, if D splits over some subfield F, then it would also split over any subfield containing F. So it suffices for us to look at maximal subfields, i.e. those that are not properly contained in any other subfield of D. It turns out that indeed, D would split over such maximal subfields. In fact, such splitting could be given as follows. So, D tensor with any such maximal subfield K is going to be isomorphic to the endomorphism ring of D over K. This endomorphism ring is going to be a matrix algebra over K because D is a finite dimension over K. Actually, if we compare the dimension of both sides, we see even more. So observe the dimension over little k of this left side is going to be the product of the dimension of this big K over little k with the dimension of D over little k. Now the dimension of D over little k is just this m times dimension of big K over little k. So this is dimension of big K over little k squared times m. On the other hand, what's the dimension of this matrix algebra over little k? Well, this has m square entry, so this has dimension m square over the big K, this blue K. Thus its dimension over little k is gonna be m square times the dimension of big K over little k. Now these numbers have to be the same, and that means that the dimension of big K over little k has to be equal to the dimension of D over big K. In particular, we see that the dimension of a central division algebra must always be a square. Thus we see that if we can establish this splitting, then we have this identity on the dimension. But the converse is also true. If we could establish these identities here, then we can also establish this splitting. This is because K tensor D is simple, so this map must be injective. Once we have this identity, we see that these two algebra have the same dimension over K, and so the map must also be surjective, hence is an isomorphism. Recall that this map is just a map that sends a simple tensor alpha tensor D to the map which is left multiplication by alpha and right multiplication by D. And why is this simple? Well, that's because the tensor product of a simple algebra with a central simple algebra is always gonna be simple. This is established in a separate video, but if you don't know this, don't worry, because we're gonna give an alternative direct proof of this splitting. We will establish both of these in one swoop by taking a basis E1 En of D over little k, and then show directly that the image of one tensor E1, one tensor En under this map is gonna form a basis for this view as a vector space over big K. Now, since the dimension of this over big K is m squared, this shows that n, these numbers of this EI, must be equal to m squared. In particular, this extension has the same degree as this extension, thus establishing these identities here. Moreover, the fact that the image of these vectors remain linearly independent here show that this map of big K vector space must be injective. So this is actually an isomorphism. So in the next video, let us see why the images of this one tensor EI are gonna be linearly independent inside this endomorphism ring. And in the video after that, we'll see why those images actually span this ring, viewed as a big K vector space. Finally, we'll see how we could generalize all of this story to the case of a general central simple algebra that is not necessarily a division ring.